Okay, so this is problem 10 of the homework, which is essentially just a simple extension of the example 6.10 in our textbook. And just to give you a recollection of what the example 6.10 is, so this example was with regards to temperature sensing. So we have small n number of sensors, each one of which is measuring the temperature y, right? So the temperature y is actually a random variable, which is being measured by n sensors, and the measurement is denoted by x sub I. So x1 through x sub n represents the noisy measurements. And the reason why they're noisy is because of this additive Gaussian noise. And each one of these noise terms, n1 through n sub n, all of them are Gaussian, which have mean zero. So zero mean Gaussian and variance sigma e squared. So they're IID, independent and identically distributed. And the specific example that the textbook had provided you with a prior on the temperature y to be a zero mean Gaussian prior with a mean of mu t, right? So this was y was known to be the temperature that you're measuring was known to be Gaussian with a mean of mu t and a variance of sigma t squared, right? And our problem here is the only change there is that the prior is no longer Gaussian, strictly speaking, but rather a truncated Gaussian. It's Gaussian only between 10 and 20, right? So in order to provide you with a solution to the specific problems that we have right over here, let me just quickly go over the solution to the problem to the example 6.10, right? So what example 6.10 stated was for you to determine the map estimate, right? So, and let me just call it at y hat, the map estimate given the information, right? So this is argument max, and you're searching over y, and you're trying to maximize y given all of the observations on the vector x. So this is y given x, and I know that this is the same as argument max over y. This is f of x using Bayesian rule, Bayes theorem. So this is the observations, all of the observations x bar given y times fy of y, right? And there's a denominator term, but that denominator is independent of y. Therefore, it has no role to play in the optimization. And from here, I can quickly say what fx of given y is. So x given y. So x given y, as you can see in the textbook as well, is given y is all independent, right? So this is 1 upon root 2 pi. So actually, let me use 1 upon 2 pi sigma e squared raised to power n by 2, because noise is IID, identical, independent, and identically distributed. And this is e raised to power. So I'm going to use exponential here to make my life easier as far as writing is concerned. So this is 1 minus 1 upon 2 sigma e squared. And then there's a summation here from I equals 1 to n xi minus y whole squared, because given y, each one of the x's is Gaussian with the variance sigma e squared and a mean equal to y. Okay, and from here, y hat turned out to be equal to is going to turn out to be equal to argument max, and you're searching over y from minus infinity to plus infinity, right? So that's what you're searching over is as far as this optimization problem is concerned. And then I'm just going to multiply the PDFs together, but ignoring the constant terms so that I simplify my optimization. So this is just exponential minus 1 upon 2 sigma e squared summation I equals 1 to nxi minus y whole squared and times the prior. Prior also has a constant term. This constant term here, which I can ignore as far as the optimization is concerned. And all I'm going to be left with is another exponential. And this is minus 1 upon 2 sigma t squared times y minus mu t whole squared. Okay, so this is the optimization that we're working with. And I mean, if you go through the textbook, I mean, this is a concave function. So you differentiate this with respect to y, and you find out where the slope is equal to 0. And it turns out that the slope turns out to be equal to 0. And I'm skipping through the solutions. Y hat turns out to be, so this is the point as far as the book example is concerned. This is the point where the slope of the objective function is 0. And this is given by 1 upon n. So I'm just going to write this expression out. So this is I equals 1 to n xi and plus mu t sigma e squared divided by n times sigma t squared divided by 1 plus sigma e squared divided by n sigma t squared. So let's say this is equation number 1, which was the solution to the map optimization problem. Okay, and one of the important point here is that when we were doing the optimization in the textbook, this y was unconstrained in the sense that we were actually searching for this y and the point where the slope turns out to be 0, which turns out to be the optima, from minus infinity to plus infinity. So implicitly, what this says is that you're searching over y for all values of y between minus infinity and plus infinity, the entire number line, if you will. Okay. Now comes our problem. Now, our problem is slightly different, is not very different, but only slightly different in the sense that for our problem, the prior has a shape which looks exactly what the textbook prior was. So this is still 1 upon root 2 pi sigma t squared e raised to exponential minus y minus mu t whole squared divided by 2 sigma t squared is still that, except that we're truncating. So it's somehow, let's say you were told that this follows a Gaussian distribution, except that this Gaussian distribution is truncated between two limits. And that limit was, for our example, was 10 is less than y is less than 20. And because it's truncated, therefore, I have to have some constant here so that it integrates to 1. N is therefore 0 otherwise. Now, this is what we're working with, right? Otherwise, the problem is exactly the same. So as a result, when we're doing for this particular problem, our optimization, so we say the y, in this case, so I'm going to use map here. And let me use a tilde here in order to ensure that this is different than the y hat that I have here, right? So this is still argument maximum or y f x given f of x given y evaluated at the observations that you made and time multiplied by the prior that you have, right? So let me just call it tilde here so that this is different from the prior that you had earlier, okay? And we see that the shape is exactly the same. The mathematical expression for y is exactly the same, except that this, so in other words, this thing here is the same shape as the example, except that it's it is 0 outside of the interval 10 is less than y is less than 20, right? So if it's 0 outside of this interval, that means when I am doing the optimization, I will only have to look for that y which lies between 10 and 20, or I would have to look for the optima between 10 and 20, because I know outside of this interval, this objective function, which is just a multiplication of these two, is going to turn out to be equal to 0, right? And because I'm maximizing, I will always, 0 is the minimum value that I could get, because these are just all positive numbers, okay? So that means I have to restrict myself. So that means this is going to turn out to be argument max. And here, the objective function is exactly going to be the same as I had earlier. So this is minus 1 upon 2 sigma e squared summation I equals 1 to n xi minus y whole squared times exponential minus 1 upon 2 sigma t squared times y minus mu t whole square. So this is the mathematical description is exactly the same, except that over here I am looking for that y which is between 10 and 20. So I'm no longer going to find a search over y on the entire number line, just between 10 and 20, right? Um, it turns out that this function is still concave. Still, this function is still concave. And if I were, so I'll take a graphical look here, right? So I just look at this like, so this, let's say this is the number line over which I am evaluating this objective function. And this is a concave function. So the concave function looks something like this, right? And let's assume the case one, which is, let's say this was y equals 10 and this was y equals 20, right? Now, what this case represents is, so the optima for this objective function is obtained where the slope is 0, and this would be this value here, right? And this is the y hat that's there in the textbook, right? So this is from the equation 1, right? And if this is the case, in other words, if y hat is between 10 and 20, right, is between 10 and 20, then I can then I'm guaranteed that the optima that's there in the textbook at which the slope is equal to 0, that turns out to be the optima for this particular case as well, right? So this is case 1, where 10 is less than y hat is less than 20, right? And this y hat is really from 1, right? That we had earlier, right? So this is case 1. And I can actually define 2 other cases as well. That's that there could possibly be other cases. What could those other cases be? For case 2, I could have had the following scenario where this was 10 and this was once again 20 on the number line, where this is y. And if I were drawing the objective function, so let me use a different color here. If I was drawing the objective function could have looked like this, right? So this was y hat. And the y hat in this case, and in this case too, is y hat is less than 10, right? And here we use the property of the concave function, which is after the point where the slope is 0, the slope is always going to be negative. In other words, the function is going to be always a decaying function, right? It's always going to be decreasing. So therefore, because of that fact, this turns out to be the optimum point because we're maximizing, right? Right. So this is your y hat turns out to be, or y tilde rather, for this particular example, y tilde is equal to 10, right? So this is case 2. Um, I can describe another case, and which is as so this is case 3. And if this is the real number line, let's say this is the real number line of y, this was 10, this was 20, and the objective function may look like this. So this is case 3, right? And this corresponds to the case where the maxima that the book evaluates, where the slope is equal to 0. This is y hat, right? So this y hat in this case is greater than 20. Once again, because of the properties of the objective function, which is a concave function, which is before the optima, the slope is always positive. That means it's always a monotonically increasing function. So in this case, this turns out to be the optima. This is y tilde map. Okay, so combining all three C cases together, this is our solution. So y, so this implies that y tilde map, which is the optima for this particular problem in the homework, are these three cases, right? So this turns out to be equal to y tilde, where y tilde is equation number 1 for the case when the y hat is between 10 and 20. This is optima is equal to 10 for the case when y hat is less than 10 and is equal to 20 when y hat is greater than 20. So this is what the solution is. So I mean, essentially what we've used is the properties of concave functions.